Okay, welcome back. I just finished writing all the rest of this stuff so you didn't have to be bored watching me type. So I'm going to run this to see if it actually works. So it looks like that's my unsorted array. That's my sorted array. Man, the number of milliseconds is incredibly low. And the while count is 1. Average count is 99. And the swap count is 0. I think there must be something wrong. Yeah. The thing is, once you've sorted it one time, this is an in-place sort, which means once you've sorted it, it stays sorted. And so these 10 tries in here are working on a list that's already been sorted. Well, that sucks. That's going to mess up our numbers. So what I basically need to do is to redo this part over again for each one of the loops. I need to have a fresh set of random numbers every time. Now, make sure you're not instrumenting that, because I don't want to instrument the filling of the array with random numbers. Okay? So if you forget this step, then none of your statistics will make any sense whatsoever. You'll be scratching your head going, well, how come it didn't work? It's because you've already sorted it. Okay, so let me run this thing one more time. Okay, so there's my original random, and then here's my sorted, and now it makes sense. The while count, the for count, and the swap count. Cool? Okay. Whew. Okay, now I'm going to show you how you can figure out which one of these things is going to end up being my loop count. Because I really don't want 3 loop counts. I really just want 1, but I don't know which one yet. You might think, well, I'm going to go for the one that's the smallest. I'm going to go for the while count. No, that's not the way it works. You need to put some thinking to it. And if you can't look at the code and figure it out, you need to be able to graph it out like in Microsoft Excel, and then you'll spot which ones are good and which ones are not. So that's what we're going to do now. So here's an Excel spreadsheet showing the size for n being 100, 200, 300, 400, 500, and 1,000. So here's the milliseconds it took, the average milliseconds. This is the while count, the for count, and the swap count. Okay, so milliseconds, it kind of goes whoop. While count, straight line. And then these other two look an awful lot like the milliseconds. So I can't use the while. Can you eyeball this and figure out that the while loop is not measuring what we want? First of all, it's linear. In other words, if that was our measure that we were going to use to figure out what the big O notation is, the big O notation here would be, well, if you have an n of 100, then an n of 1,000 will be just, 100 times more. Well, that's not at all the case. Clearly, it's not 100 times more. It's a lot more than that. So I can't use the while loop. But if you just kind of eyeball this, looks like both the for and the swap are equally well. They did equally well. They match the timing. So it's really a toss-up between which one do I want to use. Because I can't use this one because it's not measuring what I want, and so I have a choice between these two. Now the question is, which one? Is there a rule? Yes. Remember how we're trying to make these counters unobtrusive? Remember that? So which one of these gets count less? Well, it's the swap one. Which means I don't want my instrumentation to be messing with the performance of the thing I'm measuring. So if I had a choice between something that happens 4,000 times versus something that happened 2,000 times, I'm going to pick the smaller one. All right, one more time. I can't use the while because it's not measuring anything useful. I technically could use the for, but I chose not to because it's more intrusive. And so I picked the swap as my location. So now I would go back through here and get rid of the others, right? I'd comment out the while and comment out the for and just have one loop count. Okay? Cool. You guys now know how to instrument. If you can eyeball it, great. If you can't eyeball it, throw in a few, graph it, and figure out which one you should be using. It's not that difficult. Now let's go back to Excel, and I'm going to add something here. Remember the big O notation? Well, we hadn't actually got to the big O notation for the bubble sort, but trust me, it's the same as the insertion sort. So I'm going to go here and just put in something like n squared. And so this is just going to be b1 times b1. Okay? No, it's just the square of n. And I'm going to drag these across. Okay, so I'm going to do another chart. Now, pay attention, because this is how I do charts and not necessarily the way I'm asking you to do them. I'm just saying it's easy for me to do it this way. Okay? What I do is I light up the entire thing. Okay? A lot of people have more skills, and you could go in and slice and dice. I don't like that. And then I'm just going to add, now that I have them lit up, I'm going to go to Insert, go to the Charts, and there's lots of choices. I'm not just going to click on that guy. I'm going to hit the little down arrow, okay, and pick a scatter plot that has, curves on it, okay? All right. And then, so now it's plotted them all, okay? It's plotted all 5. I've got the MS, the while, the for, the swap, and the N2. Okay, I really don't want all of that. So I'm just going to do a right click on this guy and see where it says select data, okay? And I'm just going to go through and unclick the things I don't want. So it now just shows N2. Okay, so here's N2, and I'm going to put him right next to my MS guy. And so what have we just done? We've proven the formula. Isn't that amazing? The book says that the big O notation for this guy was n squared. And we've just experimentally proven that that is absolutely correct. Isn't that pretty cool? Now, if I ask you to do it in reverse, if I said, okay, what is the big O notation? That might be a little more complicated, because you probably have to do some choices. You do an n squared or an n log or an n times log. You have like 5 or 6 choices, and then once you got them, you would compare them to the execution, either the milliseconds or a legitimate loop, because in theory they should have the same curves. And then you go, it looks like it's this. Now, I'm not asking you to do that. I'm not asking you to put like 5 different possibilities for the big O notation and then experimentally figure out which one. Here I'm telling you that it's n squared, and I just verified that it was the case. Okay, is this kind of cool that we verified the formula in the book? Okay, cool. Phew. Okay, so now let's get back. Speaking of the book, let's get back to the book. All right, so best case scenario is just like before. The best case scenario is going to be everything is already sorted. And so therefore, the swap count is going to be 0. Do you remember seeing that? Right, we kind of saw it by accident, right? Cool. Worst case scenario would be absolutely everything sorted backwards, and so it had to bubble this one and move it over and move it over and move it over, and then do it over again, move it over and over and over and over and over and over. So that would be n squared again. So one more time. The worst case matches the previous one. The best case matches the previous one, and the average case matches the previous one. Now, what can you say about that? If all 3 of the big O notations match, then can you say that these 2 algorithms are computationally equally efficient? Yes, that's exactly what that means. The whole point of this class is to be able to go through, look at the notation, either derive it or prove it, and then compare that notation to one of the others and say, well, these 2 should behave the same because their big O notations are the same. Therefore, they ought to behave the same. And we're going to experimentally prove that in your term assignment, where we're going to run all different types of input cases, and then input classes with all sorts of different ones, and then prove that that is exactly the case. Okay, so there is a really, really cool YouTube video. I mean, I like this guy. It's a YouTube video on explaining the difference between a bubble sort and a quick sort. Okay, I would actually recommend you actually go to this thing and watch these guys. It's hilariously, it's actually kind of entertaining.
We'll now demonstrate insertion sort. First, let's assume the left half of our input is already sorted. We'll now add the next element to the sorted part by moving it left until we find where it belongs. We'll compare it with its left neighbor. Since the neighbor is brighter, we'll swap. We'll continue until we find an element darker than the one we're adding. This is the right spot for it. We'll now repeat the same steps with the next unsorted element. And so on. Now let's start from the beginning. The first element by itself is already a sorted sublist. We'll extend it by adding new elements, same as we saw before.
Ready, set, go! The nearsighted robot is what they call this guy, because he picks it up and has to hold it really close. Okay, so the insertion sort wins in this particular case. I'm going to go ahead and stop this guy, but isn't that pretty cool? I like this little animation thing. I'm not going to wait for it to finish. So the bubble sort should be worse, but that's not exactly what we kind of sort of determined from our experimentation. Our experimentation basically said that there were both, the average case was going to be n squared. So why is it that this guy, I mean, I'm going to go ahead and scoot to the end. Well, no, I'm not. Hang on. Where he finally finishes. Oh, come on. He goes to 42 apparently before he gets it done. 30 to 42. Now, in the big picture, the difference between 30 and 42 isn't that great. Okay, I'm just saying. That's why the big O notation is a generalization. Okay, it's not designed to predict like a stopwatch how long it's going to take to do something. Okay, that's not what it's for. It's for just making general comparisons. You remember, for example, in the discussion about we calculated out, you know, it'd be log n plus 1, except when we got to the big O notation, we just kind of ignored the plus 1 thing because it's not all that relevant. That's what we're talking about. The big O notation is the big picture. It's to show computational complexity, not predict necessarily execution time. Okay. Anyway, there's a whole bunch of these guys if you just want to go poke around and find these guys. Utaprod is the YouTube channel. Okay, so I'm going to move on to the shell sort on page 89. So it's one of those things that it's very good at making swaps that are far apart. So like these robots only just picked up one of these guys and went, oh, okay, this goes to go here. You know, that's all it did. When we get to the shell sort, it's going to say, this one needs to go way over here. So it makes huge changes in distance, so to speak. But as always, we're coming up on the 15-minute mark.